Today we start the unit on energy. The big idea in energy and why it's so useful is that energy can never be created or destroyed. It can only be converted from one form to another. The person who first realized that was James Prescott Joule. He realized as you did things to one object, for example, if you ground a hole into a piece of steel, all of that effort, all that work that you put into it, all the energy you put in, would get converted into heat, which is just another form of energy. We'll discover there's a couple of different types of energy this unit, and we're going to talk about a couple of them today. So first of all, before we get started, I have to define work. It's very, very different from the common use of the word. For example, you might say, oh, I've got a lot of work to do tonight. In physics, work involves a mathematical equation. Work is defined as force times distance, delta x, times the cosine of the angle between it. And because of the cosine, it's very interesting. We'll talk about this. Because of the cosine, if you remember, and I think I've got it on this slide, if cosine of 0 degrees is positive 1. If you've got cosine of 90 degrees, it's 0. And if you have cosine of 180 degrees, it's negative 1. So depending on what the angle is here, work can either be positive, if it's somewhere between 0 up to but not including 90, because at 90 it'd be 0. And it can be negative if it's somewhere between 0 or 90 degrees and 180 degrees. Again, slightly larger than that. And here's where it's interesting. Work is a very special thing. Work transfers energy from one system to another. If you do positive work, you're adding energy to that system from someplace else. If you're doing negative work, you're removing energy from that system and taking it somewhere else. So even though energy is conserved, you can move it from one system of objects to another system of objects. And that is what work does. Work moves energy from one thing to another. So take a quick look at this. I told you work can either add or remove energy. In this case, what's happening here? This person is pushing on this car. What's the angle between the displacement of the car and the actual motion? And we'll talk about it here as well. Here's theta on this one. The top one is a little bit hard to see, but in the top one, the angle between the force and displacement is 0 degrees. And so if you think about it, cosine of 0 degrees is positive 1. So this person is doing positive work on the car. What's happening to the car? The car is gaining energy. It's probably gaining some speed. Meanwhile, the person is losing energy. You're like, wait a second, how can we lose energy? Well, we're burning up the food energy from our breakfast, our lunch, or our dinner, the food that we ate. We're giving the car system some energy. In this case, baseball is being caught. And if you catch a baseball, you have to move your glove backwards as you're catching it. You can't just stop it instantaneously. While you're slowing it down to stop it, your hand is moving downward while you're exerting a force upward. And in this case, cosine of 180 degrees, which is the angle between the force and the displacement, if you remember from the previous slide, is negative 1. So in this case, if you do force times delta x times the cosine of this, it's going to be negative work. What does it mean? It means the ball, in this case, is losing energy. How's it losing energy? It's getting slower. It's losing the energy of motion that it had. So, the units for work. If you remember, the units for force, we've been working with that, are newtons. Displacement is meters. And so newtons times meters is the unit for work. Because it's used so frequently, it's given its own unit named after James Prescott Joule. It's called the joule, abbreviated with a capital J. Now, a couple of quick notes on this one. Force without displacement does not do work. For example, if you're standing against a wall or leaning against it and applying a force to it, it doesn't matter how much force you apply. If the wall doesn't move, the delta x part would be 0. And so the amount of work you're doing on the wall would be zero. In this case, yeah, delta x is zero. Another example is this. Displacement without a force doesn't do work. If you've got an asteroid coasting through space, deep space with in this case, there is a displacement, but there's absolutely no force on it if assuming it's far away from any object. It's got a displacement, but there's no force on it. Again, there's no work being done, and the energy is not changing. And then finally, a force that's perpendicular does not do work. So for example, if you've got a car, and we've already talked about cars on roads, but let's say it's driving on the highway. What forces are acting on it? Force of gravity, normal force, and there might be drag or frictional forces as well. But in this case, I just want to talk about this. Does the normal force do any work on it? The answer is absolutely not. Why? In this case, the normal force is acting upward. And by the way, gravity is also not doing any work on it. But our displacement is this direction. And so in this case, even though there's a force and there's a displacement, the angle between them is 90 degrees. And because of that, the cosine of 90 degrees is zero. And so there's no work being done. The normal force does not speed up or slow down the car. It does not change the car's energy. Neither does the force of gravity. Assume it's on level ground. All right, moving on. So how much work does normal force do on a block of dry ice? Dry ice, if you've never played with it, is solid carbon dioxide. It's very cool. It sublimes. I mean, it goes directly from a solid to a gas. But it's sort of like an ice hockey or like a air hockey puck, but without the air hockey table. As it converts into gas, it literally floats. And so you can give it a push and it will move basically frictionlessly across the table. That part's not too critical again, but again, this idea, how much work does the normal force do on this as it moves across the table? Well, in this case, normal force will be acting this way. I'm not drawing all the other forces. But the angle between these is 90 degrees. And so what happens here? The angle between the displacement and this 90 degrees, cosine of 90 degrees is zero. So how much work does normal force do? The answer is 0 joules. How much work is gravity doing on the table in front of you? Well, force of gravity is acting downward, but unless your table is moving downward or upward, how much work is it doing? The answer is, again, 0 joules. Why? In this case, that's a J. In this case, because delta x is 0. The table is not moving. So even though there's a force, there's no work being done. And then, this one's tricky. How much work is the sun doing on the Earth? And do you have motion? Do you have a displacement? Yeah. You've got delta x. Do you have force? The answer is yeah. The sun is exerting a force on the Earth. I'm going to sort of just draw it over at one point here. When the Earth is over here, the force of gravity is this way. The sun's pulling it towards it. And the displacement at that moment is this direction, tangent to the circle. That's what its velocity would be at that instant. Is there work being done? Well, in this case, it's a tricky question. Again, it's like the first one. Theta every point is going to be 90 degrees. At every single point in its orbit, even when, for example, it's over here, force of gravity be going this way, displacement be going this way, it'd always be perpendicular to each other. The velocity is always perpendicular. The force of gravity is always directly towards the sun. How much work does the sun do on the Earth? The answer is 0 joules. Because at every single point, the force is perpendicular to the displacement. So a couple of tricky questions. All right, now an answer that actually is not 0. Imagine you had a 1 kilogram mass and you're holding it on the end of a string. How much work does the gravitational force do on the mass? So in this case, the force of gravity on a 1 kilogram mass is going to be 10 joules. Oh, sorry, 10 newtons. Oh my goodness. Can't believe I said that. And it's going to be displaced a distance of 1 meter downward. So our delta x is 1 meter. What's the angle between these two? Well, hopefully you can see that it would be just 0 degrees. So if we plug in into our work equation, in this case, the angle between these two would be 0 degrees. So how much work is being done by the gravitational force? It would be force times displacement times the cosine of 0 degrees. I'll write it out though first so you can sort of see it. And I'm hoping you can realize it's going to be positive 10 joules of work is being done by gravity. And now, here's the second part of this one. How much work is being done by your hand? Now, I need to mention one small thing on this thing. It's being lowered at a constant velocity. What does that mean? It means the sum of the forces on it, that's my funny sigma, must be 0. So that means the tension here has to be 10 newtons so that the net force on it is 0. And the tension in the other string here on the other end, remember, is always equal. The tension here, of course, is going to be 10 newtons because remember, it's the same everywhere inside of the same rope. And if your hand is lowering it down at a constant rate, the force that your hand must be applying, I'll call it force applied, must also be 10 newtons. So how much work is your hand doing? Well, this is the force acting upward. Displacement's still downward. So this gets a little tricky. In this case, what's theta? So the first one, theta was 0 degrees. In this case, theta is going to be 180. Why? Your hand has to exert an upward force to keep this thing moving downward at a constant rate. If your hand didn't apply any force or applied a force downward, it would be accelerating. And I don't know if you can see it already, but if you plug in your numbers, 10 newtons times our displacement, 1 meter, times the cosine in this case of 180 degrees, cosine of 180 degrees, I'll write it out in this time, is going to be -1. What happens this time? The work is going to be -10 joules. So even though while gravity is doing positive work in this case, your hand is actually doing negative work. If it was only gravity acting on it, the mass would gain 10 joules of kinetic energy. We'll talk about that's the energy of motion. Because your hand's doing negative work on it, the overall energy of this thing is not changing in terms of the kinetic energy. So, some mathematics. Let's say, whoops, I don't have anything drawn on this one. If you're applying 500 newtons this way, that's our force, and you're moving the car 10 meters, forgive me trying to draw on this one, how much work do you do? And I'm hoping you can sort of see this. You're like, oh, wait, this is not that bad. So delta x is going to be 10 meters. And the angle between this, as we mentioned before, is 0. So if we plug this one in, work, and I'm not going to write it because we have it up on top here, is going to be 500 newtons times 10 meters times the cosine of the angle between those, which is going to be 0 degrees. And so if you solve it, you'll discover that the person's doing, and I know I wouldn't have to list the positive in front of this, but I will anyway, positive 5,000 joules of work. And now my second question, how much energy does the car gain or lose during this time? Remember that if you do positive work, the system gains energy. If you do negative work, the system loses energy. In this case, it's going to gain energy. How much? Well, it's going to be exactly equal to the amount of work you did. So the car is going to gain 5,000 joules of energy, which is exactly equal to the amount of work you did on the car. When you do positive work on the car, it gains energy. If you do negative work, it loses energy. All right, another example. Take a quick look at this one. Again, there's definition of work. If you've ever had a younger sibling and they've just starting to learn how to ride a bicycle, the first time they ride it, they can finally get themselves going. They're super excited, but they may not know how to stop. And so oftentimes what you have to do is get in front of them and then slowly move backwards or walk backwards while you apply a force to them to bring them to a stop. How much work do you do? Well, in this case, if you look at it, it's just going to be force times displacement. So I'm going to use this equation up here. So the work done is going to be the force, 200 newtons, times the displacement, which is 5 meters. I'm sorry, leaving off units, times the cosine of the angle between it. What's the angle between the displacement and the force? Well, force is pointing towards the left, displacement's pointing towards the right. Theta, the angle between those two, is going to be 180 degrees. So the answer to the first question, how much work are you doing? The answer is negative 1,000 joules of work. 200 times 5 is 1,000. Cosine of 180 is negative 1. So the first question, how much work do you do? That answer is this. And then finally, the second question here, how much energy does the biker and rider gain or lose? Well, in this case, remember, the work is equal to the amount of energy that system gains or loses. So in this case, it's going to lose. How much is it going to lose? Well, it's going to be exactly equal to that number again. So it's going to lose 1,000 joules. And by the way, don't get confused. When I say you lose negative 100 or negative 1,000, doesn't mean you gain 1,000. It's just the total energy changes. It's losing 1,000 joules. Don't overthink it. Last chapter, we talked about 4 types of forces. Force of gravity, normal force, friction, and tension. There's lots of other forces, including lift, magnetic forces, electrostatic forces, buoyant forces. But the same thing is true. Last chapter, we just focused on 4. The same thing's true with energy. There's lots of different types of energy. There's light energy, acoustic energy, that's sound energy, nuclear energy, electrical energy, vibrational energy. But in this chapter, we're just going to focus on the following forms: gravitational potential energy, kinetic energy, elastic potential energy, and heat. And that last one, heat, I'm going to sometimes call it energy dissipated. I'll explain why in just a moment. But again, just remember, this is one of the big ideas in this one. Work changes the energy of the system by moving energy either into that system from another system or out of that system to another system when you do negative work. So dissipated energy, real quick. Here's a block of steel hitting or being dropped on the floor in slow motion. What happens? It has a very large kinetic energy. It's the energy of motion. But as it hits, watch what happens to the vibrations of the molecules that make it up. They're represented by those little spheres. You'll notice that they start shaking faster and faster. What does that represent? That represents the vibrational motion of the molecules, which is equal to the temperature or heat of the object. What happens when you drop a ball onto the floor? You convert some of the energy into heat. Now, when you first drop an object, it can actually make some light if it hits really hard, but it can make a sound like thump hits the ground. It might make some vibrations as well. But eventually all of that, even the sound that bounces around the room, will get absorbed by clothing, by the walls, by the ceiling, by the floor. What happens to all that sound energy, all that vibrational energy, the light energy? Eventually it all ends up as heat. And so instead of saying heat right away, I tend to just use the word energy dissipated. It's just a little bit easier to say, the light, the sound, the vibration, the heat. We just say dissipated energy. We know eventually that's all going to become heat. So, gravitational potential energy, abbreviated GPE. And so oftentimes, instead of saying gravitational potential energy, we just say it's GPE. You can also represent it with U sub G. U is the variable in physics used for potential energy. And just to indicate what type of potential energy, we put a little sub G by it. So how much energy does it take, or how much energy does a 5 kilogram mass gain if you lift it 2 meters upward? So think about that for a quick moment. If you've got a 5 kilogram object, what force do you need to apply to lift it at a constant rate? Well, the force of gravity on it is going to be 50 newtons. And so if you want to lift it up at a constant rate, you're going to have to apply, and you could either do this directly by lifting it up or using a rope or string like we did in the previous case. But you're going to have to apply 50 newtons this way. And you're lifting it up. Let's say we lift it through a height of 2 meters, like we said in this one here. If delta x is 2 meters, another way of thinking about delta x is, in this case, it's just the change in the height of this thing. I'll call it delta h. Is going to be 2 meters. So how much work did we do? Well, both the applied force and the displacement are both upward. So the angle between it is going to be 0. And so if we do our work equation, remember work, W, is equal to the force, in this case 50 newtons, times the displacement, 2 meters, times the cosine of 0 degrees. And if you can't already see it, remember the work you do is equal to the energy that something gains or loses. In this case, we did 100 joules of work, which is the answer for how much energy this mass gained. We can recover that energy if we drop it. We call this stored energy or potential energy just because it's kind of a cool way of thinking about it. And now, mathematically, how can you solve gravitational potential energy? Well, it's equal, this is how much potential energy the object gained. It was equal to the work done. How do we calculate the work done? Well, we took the force of gravity, the 50 newtons, we calculated that by just taking the mass, 5, times gravity, 10, and then multiply that by delta H, the height change, which in this case was 2 meters. And so when we talk about gravitational potential energy, you just take mass times gravity, usually 10, times the height change that you're lifting it through. And the units here, again, because this is force and this is displacement, the units are still going to be newtons times meters, or again, just joules, abbreviated capital J. The one question I have is, where should you set H equals 0? When does an object have 0 gravitational potential energy? And that sounds like a strange question, but trust me on this one for a moment. Should you just measure from the floor? Well, you could, but if you think about it, your floor, you could probably take an object from the floor, and the floor of your house or school is definitely above sea level. So you could actually take it and drop it down to the nearest beach. And now you're like, okay, it's on this, the sand here right by the ocean. That's when H equals 0. Well, technically, you could drop it to the bottom of the ocean, down to the bottom of the Marianas Trench, which is the deepest part. And you might say, okay, that's as low as it could be. At that point, it has 0 gravitational potential energy. But you could even drill a hole to the center of the Earth and drop it all the way down. I'm not going to make it proportional. And you're like, okay, at the center of the Earth, that's as far as you can possibly fall. That's where H should be 0. Well, you could remove the Earth, it would fall to the center of the Sun. You could remove the Sun, it would fall to the middle of the Milky Way galaxy, yada, yada, yada. The answer is here's the strange thing. You can set H equals 0 anywhere you want. because we're always going to be working with the change in the gravitational potential, delta GPE. But because of that, you get some weird effects sometimes. Say, for example, you decide to make the ground 0. So let's say you've got a well, and you say the ground here is h equals 0. What happens when you drop an object into a well? Well, if you drop an object to the bottom of the well, technically, its height now is negative. For example, if it's a 5-meter deep well, the height is now negative 5 meters if we make the surface that. And so suddenly now, if you plug in negative 5 for h, what happens? You'll end up with negative gravitational potential energy. I should have given it a mass real quick so you could actually calculate it. But it's okay. You can have negative gravitational potential energy in any problem. The other thing I'm going to talk about real quick is the energy of motion. And some of you might have learned this in middle school or perhaps in chemistry. Kinetic energy, abbreviated again with just an acronym KE, as KE, or you can just do capital K. It's the energy of motion. Any object in motion has kinetic energy, and the formula for kinetic energy is just 1/2 mv squared. 1/2 times the mass of the object times its velocity squared. The units, again, are Newton meters. I'd have to prove it to you. And again, we can just use joules. Take a quick look at this one. You've got a 50-kilogram or athlete, say it's a football player, who can run pretty doggone fast at 10 meters per second. That's world record sprint speed. Or you've got an athlete that is twice as massive who can only run half as fast. I'm not body shaming here. I'm just trying to make them look bigger. Who has more energy? And you're like, oh, wait, this is easy. Double the mass, but half the velocity. They have the same energy. Well, if you check it real quick, there's something interesting going on here. Sorry, meters per second. Because of the fact that the v squared here, the one who has more velocity, in this case, the 50-kilogram one, is actually going to have more energy. And you could check it out real quick, but in this case, mass times velocity is the same for both. But because velocity has a bigger impact on it, our 50-kilogram person actually has more energy, and it would hurt a lot more if they ran into you. At this point, you should be saying, all right, yeah, okay, that's nice, but what good is energy for? Well, take a look at this problem. If you apply a force of 10 newtons for a distance of 2 meters to a 10-kilogram object that's initially at rest, what will be its final velocity? Well, first of all, draw it. You've got a 10-kilogram object. You're applying 10 newtons to it through a distance of 2 meters. And I guess it's, okay, initially starting at rest. And the question is, if you solve this, it gets pushed the distance 2 meters, what will be its final velocity? Well, you could do what we've done up to this point. You could use the equations we used in the previous chapter and solve this. How would you do it? You first do F equals mass times acceleration, F equals ma. And if you plug it in, the force on it is 10, the mass is 10 kilograms, and you could very quickly figure out, okay, the acceleration of this thing is 1 meter per second squared. And you're trying to find the final velocity, you're like, okay, all right. So you solve that. How do you find the final velocity? Well, you'd have to use one of our old equations. In this case, since we don't have time, you could use this equation, v final squared equals v initial squared plus 2 times the acceleration times delta x. And if you solve that, and you little have to plug in everything, we're trying to find the final velocity. Initial velocity is 0. And the acceleration we just found was 1. sorry, it's plus 1, times our displacement, which is 2, and you'd end up with v final squared equals 2 times 1 times 2, or 4. Taking the square root, you discover that the final velocity is just 2 meters per second. And you might say, oh man, Mr. Clymer, that sounds like one of those hard problems we had last chapter. Yeah, it's pretty hard. It'd be nicer to have some easier way of doing that. And that's where energy really comes in handy. How much work was being done on this thing? Well, work is just equal to force times displacement times, so I guess I probably should write it out, times cosine theta. And I don't know if you can see it real quick here, but we know the force is 10, our displacement is 2 meters, and the angle between these is 0, so the work done is just going to be 20 joules. You're like, okay, that's nice. How does that help us? Well, in this case, we know that our system is going to gain 20 joules. Remember, that's what work means, and I guess I should put a little positive sign by it. What type of energy is this object gaining? Well, it's gaining kinetic energy. How much kinetic energy? 20 joules worth. So I'm just going to set 20 equal to 1/2 mv squared. And plugging in our numbers, the mass of our object is 10 kilograms. So we end up with 20 equals 1/2 times 10 times v squared. And 1/2 times 10 is 5. Dividing both sides by 5, we end up with v final, or the final velocity squared, is equal to 4. Or again, that's interesting, 2 meters per second, which is the same answer we got before. Which is easier? I think energy is always easier than using multiple formulas to get there. You're like, Ms. Clymer, there still was a lot of writing. Yeah, I know, but you'll get used to this. And if you figure out the amount of work done, that's always going to be equal to the change in energy. And you just have to figure out what type of energy it's gaining. So let me get you started on what you'll be working on tonight. We're going to work with pi graphs in this first part. Remember, energy is always conserved. It just gets converted from one form to another. In this case, we have a roller coaster. And it's going to start out with a velocity of 0. It's at the top of a hill. The numbers over here represent the height in meters. How tall the hill is, basically. So it's going to start out at a height of 30 meters with no velocity, and it just starts sliding down. What type of energy does it have at point A? Well, at this point, it's got height, but it has no velocity. I would argue that at point A, it's all gravitational potential energy, GPE. But what about at point, whoa, I drew it away too fast. What about at point B? And I need you to think about it for a brief moment. What happens at point B? When you start going down a hill, you start gaining velocity. Where does that energy come from? Remember, we're gaining kinetic energy. What's happening here? Well, we were at 30 meters to start out with. By the time we're here, we're only at 10 meters above the ground. We only have what fraction of the original gravitational potential energy? Remember, gravitational potential energy is equal to mgh. What's happened to our height? Well, it went from 30 to 10. So I'd argue at point B, we only are going to have a third of our pi graph is now going to be gravitational potential energy. Where'd the rest of the energy go? It went into the form of motion, energy of motion, which is kinetic energy. What about the very bottom? At the very bottom, when the car is here, we have height equals 0 at this point. And our car is going to be moving very, very rapidly. We're saying this is h equals 0. Does it have any gravitational potential energy at this point? The answer is absolutely not. What does it have? It's got a large velocity. It's when you're going to be moving the fastest on this ride. So at point C, all of the energy is in the form of kinetic. All the energy we started out with, some of it gets converted into kinetic here at point B, and then by the time we're at point C, all of it's in the form of kinetic. And then finally, at point D is kind of a weird situation and something, it's going to lead us into what we're going to talk about next time. The car hits a spring, which briefly stops it. And so our velocity goes back to 0. And you're like, whoa, wait a second. The velocity was 0 when we started out, but we're not to the same height. We're only at 20 meters. Well, first question, what fraction of the initial gravitational potential energy, what fraction of the height do we have at point D? The answer is, at this point, I'm hoping you can sort of see it, we're back to 2/3 of our energy is gravitational potential energy. Where'd the rest of the energy go? Because there's no more kinetic. Well, this leads us into our new idea. The spring right here gets compressed, and it briefly stops the car. All the remaining energy is stored as what's called elastic potential energy. I know we haven't talked about this yet, but it leads us into this idea that you can also store energy in springs. And so by logic, we end up with this. So I want to do a couple problems with you from your worksheet, just to get you started. So here's a worksheet 4.1, and we've got a wound up toy is wound up, then walks across the table and comes to a stop. So this vector down here represents its velocity. First it's moving really fast, then it moves a little slower, and by this point here, velocity is 0. Where'd all the energy go for a wind-up toy? All wind-up toys eventually just kind of come to a stop. Where does it go? Well, at point A, let me label this as A. At point A, we've got lots of kinetic energy. At point B, we have less kinetic energy. And at point C, we have no kinetic energy. How do we solve this one? Well, I'm going to start out with all kinetic energy for point A. I'm just going to say it's got all of its energy is kinetic. The spring inside of it is already unwound if this is a wind-up toy. Whoops, should actually be drawing in black. And all of it's now in just the energy of motion. By the time it gets to point B, we have less kinetic energy. But where did it go? And I'm going to say, and just this is a complete guess, these are qualitative graphs, which means they don't involve numbers. I'm going to say that its velocity is half as big as it was before, which means kinetic energy, remember, which is 1/2 mv squared, is going to be about 1/4 as big. Where'd the rest of the energy go? And some of you already guessed it. It's not gravitational, it didn't gain any height. It's not elastic, there's no spring that we know of that's getting wound up. It ended up as just energy dissipated, which I'm going to write as E sub dis. That is heat, sound, vibration. As this rabbit is moving across the table, that eventually is all going to be in the form of heat. What about at point C? It has absolutely no kinetic energy anymore. Where did all its energy go? At this point, it's all E dis. This is one of many solutions, but probably the most logical one. And now take a look at this one. A super ball is dropped and bounces up and down. Do a pie chart for each position of the ball. So I'm going to call this position A. And then B is where the ball hits the ground, gets compressed, it acts like a spring, and then it bounces back up to point C, but not quite as high, hits the ground again at point D, and then at point E it bounces up again, but not as high. If you drop a bouncy ball on the floor or a basketball, it never goes back up to the same height. Why? Every time you compress a ball, acts like a spring, it warms up a little bit. If you've ever taken a tennis ball or a racquetball and just squeeze it back and forth in your hands a bunch of times, it warms up. In fact, tennis players will do that to kind of warm up the ball, and racquetball players as well. So, at point A, I'm going to say it's all gravitational potential energy. Why? I'm going to say that at the point we have it here, it's at the very top of its path. I'm going to say the velocity is 0. Some of you might say, Ms. Clomber, it's a parabola. That means it has to be moving forward this way. I'm going to pretend that this is almost straight up and down. What about at point B? At point B, its velocity is 0 again. In fact, at all these points, its velocity is 0. At the highest point of its path, its velocity is basically 0. Where did all the energy go at point B? Well, the ball is compressed like a compressed spring. So it's going to be elastic potential energy. But remember what I told you every time a ball gets compressed? Part of it's going to be converted into heat. So some small fraction of its E dis. You might ask me, wait, how'd you know exactly what fraction? I didn't. I just want to show that some of it gets converted into that. You could make it a quarter, you could make it a half. Your choice entirely. These are qualitative. And now, does it lose any more energy as it goes from this point back up to here? The answer is probably not. It's only when it gets compressed that we lose energy. So at point C, when it gets to the very top, same amount of gravitational potential energy, the same amount of E dis that we generated when it hit the ground here. No more, it's not generating any more E dis as it goes up. And then at point D, it hits the ground again. What's going to happen? It's going to warm up even more, which means we have more E dis and less elastic potential energy. And then finally at E, it goes back to gravitational, but we haven't made any more heat. It's only when it hits the ground and compresses that we convert some of our energy into heat. And so a larger and larger fraction of our graph gets converted into heat each time it hits the ground. Please remember the exact percentage here is entirely up to you, so don't panic. This one, last one I want to do with you. A truck is being driven at a constant velocity down a street or a highway. And here we've got points A, B, and C. The velocity is the same at every single point. And so you might think, oh, okay, it's that. But think about it. Is that really what's happening? Can you drive your car or truck forever? The answer is not really. So what's going on here? Well, here's point A, here's point B, here's point C. The velocity is constant, but how in the world do you keep your car or truck moving at a constant velocity? And here's where it gets a little fun. Don't freak out. I'm going to argue that the kinetic energy is actually constant, but what's happening is this. The KE is constant, but you're slowly converting some of your energy into heat. And you're like, whoa, 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 what in the world is this? This is chemical potential energy. Remember, U represents that. And you might say, whoa, what in the world is that coming from? Well, if you've got a gas-powered car or a diesel-powered car, it's coming from the gasoline or the diesel fuel. If you have an electric car, it's coming from the chemical potential energy stored in your batteries. What's happening as you go down the road or a highway at a constant velocity? You're slowly burning up that chemical potential energy by either burning your gas or discharging your batteries. And so what's happening to that energy though? Well, everything, all the gas you put in your tank, all the electricity you put in your battery, eventually ends up as E dis or heat. Your car is just a very efficient heater. The kinetic energy is remaining constant, but you're slowly converting the energy stored in your battery and your gasoline into heat. Eventually, you'll use up all of your stored energy. It'll all be dissipated, and eventually you're going to hit the brakes, and even the kinetic energy is going to just end up as heat in your brakes, or potentially back or recharging your batteries if you have an electric car. And so here's the worksheet. It's got a bunch of examples. We already did number 2. We did number 4, and we did number 8. Your homework tonight is finishing off the rest of this worksheet, as well as a couple of textbook problems. You can work by yourself, or you can work with your neighbor, but do make sure that you all understand it. Please realize there are multiple possible answers to each one of these. Good luck, and we'll talk to you soon.